Much like how a lot of the different branches of mathematics we use today had a common origin in the Mesopotamian area of the world, like 4,000 plus years ago. The reason we needed those branches of mathematics, there's also like a common reason for that, and basically it's our desire as humans to be able to either quantify something or understand something in the world around us. I understand why something is the way it is. A real basic example of that is like if you could imagine you had a farmer. So it was like a farmer many years ago, like thousands and thousands of years ago. There's been farmers all through recorded history, and let's say they wanted to know how much feed they would be necessary to like feed so many cattle, like some number of cattle throughout the winter months. Well, they don't just guess; they know approximately how much food each cow or each animal needs, and then they multiply, right? So like there was a need for that. Um, that's a super basic example, and you might not believe me when I say this, but like there's also a reason why if we had a triangle, we would need to know what's the relationship between the different side lengths. And like if it was a right triangle specifically, like that's how Pythagorean theorem came about is somebody's desire and need, like a necessity for knowing like what is the relationship between the two legs of a right triangle and the hypotenuse. And so if you can accept that, like there's a lot to be learned here, and over time, math has really evolved. It's become very much a language we use to understand and make predictions about the world around us. I'm recording this video April 1st, 2020, and I'm a high school math teacher in the United States. And very recently, all it was announced that pretty much every school in the country is going to be closed for the rest of the semester, rest of the school year. So we're doing this remote learning thing, um, and the reason for that is, of course, the COVID-19, the disease caused by this SARS-CoV-2, the coronavirus, novel coronavirus. And here's a graph here. So this graph is just it's the cumulative confirmed cases of this disease in different countries ever since there was 100 cases recorded in that country. And you can see that there's different colors, different countries here represented differently. And notice the data for the United States is on this trajectory here. And if you were ever watching the news and around this time, it's a very common term for you to hear is exponential. So we have this like exponential growth happening with this virus in our country. And so, well, is it really exponential? Like, can we just look at this graph and know that that's exponential? Well, not really. Like, there's like more analysis to be made. Um, so here, like, if we look at that graph, okay, and we say, here's all the data. This data here matches up with this graph. The data that this Johns Hopkins University, you can get that data right here on this website, and and we can do something where we can kind of make these dots, and even before that, right, we can put in a really basic exponential function. This is just a base to some power, and that base is like a constant base. It's something called a common ratio, and then we raise it to some power. And this b here just provides the offset in the number of days. And so if I turn this graph on, right, I have this black graph here, and I kind of tweak these numbers, you can see, all right, well, what would this need to be in order for this to line up? And again, this is modeling a perfect exponential function. There's nothing complicated going on here. It's very simple. And so as I change this, you can see that the curve gets kind of steeper, and here it kind of gets a little more flat and stuff. But I can kind of guesstimate that it's somewhere in this area. And we can even go a little farther, right? Because we have this tool at our disposal as mathematicians called regression. Regression, another word for that, a more common word sometimes, is line of best fit. And so here's the data that this graph is created by. This data, again, I got from the Johns Hopkins University COVID-19 website. And so I typed in all the data that they had for the last 30 days. This is the day number and the recorded number of cases for that day. And I could perform a regression. And again, notice that there's a lot of similarities between this right here, this function right here. Well, this is called a regression in Desmos, and then this right here. This is the same format. And if I turn that on, well, I get this black graph. And what that black graph is saying, well, that is a perfect exponential function. And as far as it knows, it's trying to match this black curve up to these green dots. And if it matched perfectly, we would have an exactly exponential. And if there's any hope here with our situation, it looks like maybe, just maybe, we're kind of deviating a bit from that possible exponential function. Maybe it's starting to flatten out. Like, so what can we do? Well, I mean, we can examine data that's from all these other countries, and we can plug that in and incorporate that into our models that show different kinds of, like, different factors that have to do with the growth of this disease. Um, and we can do that. And this seems like a really complicated, long-winded way of explaining why math is important. But it is important. Perhaps its most important part is our ability to predict things. And the way we tend to predict things, the way we do that is through the use of something called a function. I'm going to take you back to this really basic explanation of what a function is. So if I have a function, the notation for that is a function f of x, where x is the independent variable. And let's say I want this function, I want all the inputs x of this function to be squared. So essentially what this function is, it's a square function. And let's say if I wanted to move this graph down one, right, I would just subtract, these are y values vertically and x values horizontally. And so if I wanted to move the graph down one, I would want to subtract from the outputs of this function. So the outputs of this function is whatever x squared equals. And you could also say the outputs are just f of x, right? If I subtracted 1 from that, well, I would have this. And we can verify that by knowing that this is x squared and minus 1. So that red graph and that black graph are the same graph. Okay. So by subtracting 1 from the output of a function, we can produce this shift of 1 down. Okay. What if I instead I wanted to move the graph 1 to the right? Well, in order to do that, I would need to subtract 1 from the input, from the x values. I'd want to move them 1 to the right. So I could say, all right, f of x minus 1 should move this graph 1 to the right. And we can see that. And we can even verify it again by going x minus 1 quantity squared. Now notice, right, x minus 1, that's the input. So I plug it in for this x right here is the same as this right here. We can see that the blue and the black graphs are the same. And beyond these horizontal and vertical shifts, those which are called translations, we can also do other things to a function simply by multiplying by different things. So for example, also if I want to combine a horizontal and a vertical shift, like I say I want to move this up 1, right? That's both a horizontal shift of 1 to the right and a vertical shift of 1 up. Well, what if I wanted to take the original purple graph there, and let's say I wanted to make it taller? Well, this would be multiplying all the y values, all of these outputs. So, for example, there's one point on this graph, it's 0, 0. And we also have this point 1, 1, right? So there's a point 1, 1. If I were to multiply all of those outputs, all the y values by 2, well, all that did was 0 times, 0 times 0 is, 2 times 0 is 0. If I go to 1, I should be at 2, and I am, okay? And so that's multiplying all the outputs. I can also instead multiply the inputs. If I wanted to make this graph kind of narrower horizontally, I'd be multiplying all the inputs by 2. So I would be saying, all right, now everything that, like, you can imagine if I made this, instead of it being x squared, I made it 2x. So let's just plug in a number for x. Like if it was 1 squared, it'd be 1. If it's 2 squared, so if I multiplied that by it would now be 4. So if I go to 2, if I was at 1, right? If I made it 2x, now that 1 is going to be 4 instead of it being where it was before. And so these are different reasons. Sorry, I would have been at 1 before, right? These are different ways we can adjust the graph. If we want to flip the graph, if we want to make it upside down, we can just multiply everything by -1, right? If we want to actually if we want to take this one, let's say we took this one here and we wanted to, let's refresh our memory what that one looked like. Let's say I want to flip it across the x-axis, meaning make all the x values now negative. Well, I just put a negative right there instead. Put a negative. Oh, that didn't work. So I need to make that -1. Should have that be a plus. That needs to be minus now. Because by multiplying by a negative, I did the exact same thing as before. So I shifted it the other direction. So that flips it horizontally, right? Making the input, the value of the input, making that negative, making the output negative. That flips it upside down. And so those are all the different things we can do to a function. Now let's look at like an example of this in the real world. All right. Recall that what I said at the beginning of the video is that we observe things in nature and we want to come up with a way to explain them. So there's a website you can go to here, and it's on the U.S. Naval Observatory website. And if you click this button here, duration for daylight and darkness tables for 1 year, if you click it right now, as of April 1st, 2020, it doesn't work because this website is undergoing renovation and should be done by April 30th, 2020. So it doesn't work, and click the link. But what you get from it is this information here. You can basically plug in longitude and latitude, so like a GPS coordinate of your location on Earth, or you can type in a city, and you get this data. It looks like this. And what this is this is the data for January. January 1st, there were 7 hours and 57 minutes worth of daylight that day. So the sunrise to sunset, that time duration was this. And you can see that it changes all throughout the year. So at the end of January, it was 9 minutes and 7 seconds. At the beginning of June, it was 9 hours and 7 minutes. At the beginning of June, it was 16 hours and 17 minutes. And then the end of June, it was 16 hours and 33 minutes. Right? But it looked like it had a peak right here in mid-June of 16 hours and 37 minutes. And then by the end of December, it's back to low numbers, right? 7 hours and 56 minutes. So what would happen, right, if I took all these data points and I plotted them? So that's what I did here, right? I took all of this data and I copied and pasted it, and I put it into Desmos here. So this is what it looks like when you graph that data, and you can see all these dots. This is the first day in January, and then this is like in the middle of June, and then over here is like the end of December, or the end of December. So what is this? Well, you can do a similar thing. You can do this line of best fit, and it produces this graph. And you can, if you zoom out really far, you can see that graph would go on forever. And this would represent very plainly, this is the winter and this is the summer, and this is the winter and this is the summer, and this is the winter, and year over year, like the amount of daylight on a given date does not really change. Like our location, like depending on where you are and fixed location on Earth, like the amount of daylight that place receives year over year is it's basically a constant. And we can use this regression and we get these numbers here, right? And so the challenge then is to take these numbers, which are kind of abstract by their nature, and interpret what they mean given the context. So this data represents the number of hours of daylight on a given day of the year. And what we've done is created this function here, right? I can just say that this is f of x. We've created this function that models that data. So what is the value of this? And more specifically, what is this number here? What does it correspond to when I think about this graph? What does this number do? Right? And think about what we talked about with transformations of functions. What does this number do? What does this number do? Like, what does this actually mean? I know that it must shift the data up by 12.1189, right? Because I'm adding to the outputs. But like, what does it represent? What's the significance of this? And so, if we compare this, actually, we can compare this to the most basic possible version of that same function, and we can see it's drastically different. Like, it goes from this function here to this function here. So, if this function had a point right there, how come this one over here has a similar kind of point in maximum way up here somewhere? And so that's what I want you to do, is think about what do each of these individual numbers represent. What does this negative 2.08817 or 71 represent? And we'll pick up that discussion again in the next video.